Okay, in this part, we're going to discuss the topic of modeling. Modeling is a process to find a way to define the relationship between the input and the output of a system in a mathematical way. And so on this diagram, if you look at the middle of the block diagram, we have a system that is a plant for you to control. If you apply input to it, and the system will respond to that input to give an output. If you give another input, it will give another output. The question here is, can we actually find a mathematical expression of that input-output relationship? If we have a relationship in a mathematical way, then we can actually find a response for any given input. So if you change your input, we don't have to go to the system and try. We can tell what system would behave in a certain way. So that process is known as the modeling. Now, for example, in this case, we have a mass. Now, suppose this mass is floating in a vacuum condition. So there's no air resistance, there's no friction of any kind. Now, if we apply Newton's law to it, okay, and in this case, the little circle in the middle is my object, and I apply a force to the object, then the movement of the object is the output. The output of the object follows the Newton's law, or Newton's second law, i.e. F equals to ma. That's mass times acceleration. That's the equation I have there on the left-hand side. M times derivative of the velocity equals to the force applied to that mass. So in this case, input is F, which is the force. The output is the velocity of that mass. If I modify that equation slightly, I divide m to both sides and then integrate that dv dt. It becomes the equation on the right hand side. So v equals to 1 over m integration of f. Now, so for any input f, I integrate that f, divide by m, I get v. I don't need to do experiment, or I don't have to do experiment as long as I know the value of m, or the weight of that mass, and I know the profiles of the input f. Now that equation, either this equation or that equation, is a mathematical model of that system. Okay, it's a simple system, it's a single mass, and the input is f, the force, the output is v, the velocity of that movement. Now, of course, in real life, we don't have a vacuum condition. And if you have a mass, once the mass starts to move, you get some air resistance to it. Or if the mass is sitting on a surface, then there will be some friction to it. Okay? Now the friction opposes the movement of that mass. That's indicated in that red arrow. So I have a force there, or resistive force, which is proportional to the velocity. B is a constant. Now this time, if you apply Newton's law, it is the total force, which is F minus the resistance force, equals to ma. Okay? And so it becomes m times dv dt equals to F minus bv. Now move the bv to the other side of the equation, you get that. Now that's a very typical first order differential equation. And it's also a representation of a typical first-order system. And it defines the input-output relationship. So the input is F, the output is V. For any given F, and you can solve that differential equation, first-order differential equation, you find the solution V, which is in response to whatever input you apply. So that is the model of that system. Okay, slightly more complex than the previous case, which is a pure integrator. Another example, if I go a step bit further, from first order to a second order, here we have on the left-hand side a mass connected to a spring, a damper. These two, spring and damper, are connected in parallel, and at the other ends of the spring and damper are connected to some kind of reference or fixed point. Okay? Now, if I apply force as this red arrow applies, if I apply force to that mass, okay, now the mass will start to move down. If I reduce force, the mass will go up. Now, of course, this mass has to overcome the reaction forces produced by the spring and the damper. Okay, the force in the spring is proportional to how much the spring is compressed. Now, that is proportional to the displacement of that mass. Okay, the force in the damper is proportional to the relative velocity of the two terminals of that mass. Again, it's a velocity, so if displacement is x, then velocity will be x dot or dx dt. These are the two forces are represented in my equation number 1 and equation number 2. So force in the spring equals to k times x, where k is a spring constant. The force in the damper is proportional to the relative velocity of that mass. The c is a damping coefficient. So I have two forces here. This is actually oppose the movement of that mass. The total force of the three, F minus this force minus the force in the damper, equals to ma. The displacement of the mass is x. A would be the second derivative of x, or x double dot. So it's m times a equals to F minus the total of the two resistive forces, or opposing forces, Fs plus Fd. If I substitute equation 1 and 2 into here, so Fs is Fx, Kx, Fd is Cx dot, and I move these two terms to the right-hand side, left-hand side, from right-hand side to the left-hand side, I get that. I get this final equation in that box. So it's m x double dot plus c x dot plus k times x equals to f. In this case, f is my input, x is my output. It is a second order differential equation. Therefore, the system is actually a second order system. For any input, F, if you apply a force, if you know the force profile, what the force looks like, you can solve that second order differential equation to find out the response, i.e. to find out how this mass moving up and down. And of course, we are not keen normally to solve second order differential equations. First order is manageable, second order gets a bit complicated, but in other cases you might get even higher order. But that's a subject of another discussion later on, because we have an alternative way of solving differential equations. Okay, but I will leave that for later on. So that's really the modeling process I only use this as an example because for different industries, you will have different ways of finding this relationship. Electrical engineers, for example, will have electrical circuits to deal with. So they have to know the properties of inductors, capacitors, resistors, electrical motors, that kind of stuff. Mechanical stuff, engineers will need to understand the kinematics, dynamic behavior of systems, Newton's law, that kind of stuff. And then process engineers will have their own subjects to discuss. And that, of course, is subject specific. And as control engineers, we probably won't be able to know everything. So the modeling itself is just an introductory part to illustrate the process rather than the technical details. But from the once we get the differential equations, then we can start looking at these differential equations and say, now I'm taking over as a control engineer. I'm starting looking at these equations or examine these equations to see what properties we have of these systems. Okay, so first thing we're going to look at is whether a system is linear. And we have to make a judgment whether a system is linear or not by checking a set of rules or principles. Now the reason why we want to check whether a system is linear or not is because the most mathematical or most design tools we have for control systems are only applicable to linear systems. And unfortunately, in real life, many systems can be approximately described by linear systems or set of linear systems. So we can actually use these tools. Okay. Now, how to define, how to examine, or how to determine whether a system is a linear system or nonlinear system is fairly straightforward. A linear system is a one that where the principle of superposition applies. So what does that mean? For example, if you look at that lookup table on this slide, I have the input on the left-hand side, I have the output on the right-hand side. Now for a system, if you apply an input, say U1t, you will get an output. If you apply a different input, say U2t, you get a different output, Y2t. Now that applies to any system, because if you apply input, you get one output. If you apply a different input, you get a different output. Now, a linear system, for a linear system, if you add two different inputs to form a new input to the system, then the output response will be the response of these two individual inputs added together. Now, if that is true, then you have a linear system. If not, then you have a nonlinear system. That's one way of doing it. Or say, if I have an input, another way of doing it is that if I have an input U1t, I have an output Y1t. Okay? Now, if I multiply U1t by a constant, just say amplify that value to a certain value, say it's A times U1t. Then the output of the new input will be the original output YT times A. Okay, as well. If it's that stands, then you have a linear system. If not, then you have a nonlinear system. Okay, so two ways of doing it. Apply one input, get one output. Apply a second input, you get second output. If you add two inputs together, then the output should be able to add together. Or you multiply input by a factor of A, and the output should also be multiplied by the same factor. If that applies, then you have a linear system. Okay, I'm giving you a few examples here. In this case, I have a system, a first-order system, where the input-output relationship is defined by equation number 1 in the yellow block. Okay, so x is my input, y is my output. That's a 3y dot plus 4y equals 2x. I need to determine whether that system is a linear or non-linear system. So I'm going to apply the first approach. So let's assume I apply an input x1 to that equation, and I get y1. Okay, so that gives me equation number 2. So x1, y1, y1 dot. No, that's the same as this. Let's say we get it's one system we have here. So if I apply x1, we get y1, and of course that differential equation will stand. Let's change the input to x2. Suppose for this time, this same system will give me a y2, a different output because the input is different. So I get 3y2 plus 3y2 dot plus 4y2 equals to 2x2. Then of course I can say, right, I have another input x3 that leads to the output y3, and this equation also stands. Now the question comes, if I make y3 equals to, if I make x3 equals to x1 plus x2, if I make that, would my y3 equals to y1 plus y2? If that's true, then we have a linear system. If not, we have a non-linear system. To check that, the way we can do is to say, right, I have 3 equations here. I'm going to use this not for last, but I'm going to look at equation 2 and equation 3 first. I'm going to add equation 2 to equation 3, left-hand side to left-hand side, right-hand side to right-hand side. Okay, so 3y1 dot plus 3y2 dot, that's 3y1 dot plus 3y2 dot. 4y1 dot plus 4y2 dot, that's 4y1 dot plus 4y2 dot. On the right-hand side, I have 2x1 plus 2x2. So this gives me equation number 5. I can reorganize that equation a little bit because I have y1 dot, y2 dot. The dot is not very visible here, but there's a dot on top, okay? Because there's a common factor of 3. I can take that 3 out of the bracket, so that becomes 3y1 dot plus y2 dot. And then the next 2 terms, I have 4y1 plus 4y2. Again, there's a common factor of 4. I can take that 4 out of bracket, so that becomes 4 bracket y1 plus y2 close bracket. On the right hand side, I have a common factor of 2, so I can take this 2 and that 2 out of the bracket. I get 2, then brackets x1 and x2, so that gives me equation number 6. Now, equation number 6 is useful because I have x1 plus x2 on the right hand side. That's my x3. Okay, that's my assume x3. So I need to see on the left hand side if I have y3 as well. Now if I look at this, I have 4 times y1 plus y2, that's y3. I have 3y1 dot plus y2 dot, or y1 plus y2 bracket dot, that's y3 dot. So compare equation number 6 to equation number 4, these two are direct conversions. So if I replace y3 by y1 plus y2, y dot y3 plus by y1 plus y2, x3 by x1 plus x2. Let me just repeat. If I replace y3 dot by y1 dot plus y2 dot, replace y3 by y1 plus y2, and replace x3 by x1 plus x2, I get exactly same as equation 6. If they are exactly the same, then we have a linear system. So this system defined in equation number 1, or the first order differential equation number 1, therefore is a linear system. For the same system, I can use a second approach as well. Okay, I think it is slightly simpler. Okay, so in this case, I have equation 1. That's my first order differential equation for the system. Let's assume I have x1 as the input, y1 as the output. Therefore, I have this equation just by replace x by x1, this is y1, this is y1 dot. I get equation number 2. And of course, if I assume a different input, y2, I will get a different output, y2. If I assume a different input, x2, I will get a different output, y2. Now, of course, that's the same system, same differential equation, so this equation number 3 stands. So 3y2 dot plus 4y2 dot equals to 2x2. Now, let's assume, say, if I set y2 as a factor of x1, i.e. a constant times x1, would y2 be the same factor times y1? If that stands, then we have a linear system. Okay? So we need to check and make sure that happens before we can say whether that system is linear or not. Now to check that, I'm going to use equation number 2. That's for the x1 input and the y1 output. I'm going to multiply both sides by a factor of a. Now a is any constant. It doesn't really have to be a specific number. Okay? So multiply this by a, this by a, and this by a. So every single term has to be multiplied by a factor of a. So this becomes 3a y1 dot. This becomes 4a y1. This becomes 2a x1, which is by equation number 4. Okay, I'm going to reorganize that equation a little bit. I'm going to take the 3 out of this, and I put a bracket there. That becomes a y1 dot. I'm going to take 4 out of the second term in equation number 4. That becomes 4 times bracket inside bracket is a times x1. That equals to 2 times bracket a x1. Okay. Now, if you compare this new equation, equation number 5 to equation number 3, okay, compare that to this, I get x2 equals to a x1, y2 equals to a y1, y2 dot equals to a y1 dot. Therefore, y2 equals to a y1 dot. Y2 equals to a times y1. So that stands. Therefore, my system is linear. Now, when you make comparisons between this equation, equation number 3, and equation number 5, you have to make sure every single term has that relationship. Okay? If for any of the terms doesn't have that relationship, then you don't have a linear system. Okay. I'm going to give you an example of a nonlinear system, a system that is not linear. Okay, using the second approach to check. Okay, so the system in this case is defined. I'll change the system a little bit more. Okay, from 3y dot plus 4y equals to 2x to 3y dot plus 4y squared equals to 2x. Okay, just a small change, but it will make that system nonlinear. Okay, so my checking process is the same as before. So I'm going to apply x1 to the system. I get y1. Therefore, I'm just changing x1 to x to x1, y to y1, y dot to y1 dot. That gives me equation number 2. I'm going to assume a different input, x2. That will give me an output y2. And again, that equation applies. So I get 3y2 dot plus 4y2 square equals to 2 times x2. That's my equation 3. That's fairly standard. Now the next step is the key. So let's assume x2, if x2 is a factor of x1. Okay, so x2 equals to a constant times x1. Would y2 also equals to a times y1? Okay, so that's the key to check. So to do that, I'm going to multiply a, the constant, to both sides of equation 2. Okay, every single term needs to be multiplied by a. That becomes a3y1 dot equals to a4y1 square equals to a2x1. I'm going to take the constant, the 3, 4, and 2 out. Okay, that becomes 3 ay1 dot plus 4 ay1 square equals to 2ax1. Now I can compare. I can compare equation 3 to equation 5 to see if every single term matches these two conditions. x2 equals to a times x1, y2 equals to a y1. Okay, so on the right hand side, I have 2x2 in equation 3. I have 2 times bracket a x1 equals to equation 5. So that stands. See, x2 equals to a times x1, which is good. On the left-hand side, the first term is 3 times a y1 dot in equation 5. In equation 3 is y2 dot. So y2 dot equals to a times y1 dot, which is also good because y2 equals to a y1. Therefore, y2 dot equals to a is a constant. So y2 dot equals to a times y1 dot. So that first term on the left-hand side also matches. The problem comes with the second term on the left. In equation number 3, I have 4 times y2 square. In equation number 5, I have 4 times bracket a y1 square. Now, a y1 square is not the same as a y1 bracket square because y2, if y2 equals to a times y1, then y2 square needs to be a bracket times y1 square. That will make it a square times y1 square. Okay, so if that a was a square, then we have a match. Because a is not a square, so the second term between equation 3 and equation 5 actually does not match. Therefore, we have a nonlinear system. So it's fairly straightforward process. It needs a little bit of math skills, but nothing beyond your abilities. I have a slightly more harder question example here, but it's the same principle. It's a second. This time it's a second order differential equation. I have more terms on the left-hand side, more terms on the right-hand side. But the process of checking is the same. Okay, let's assume, for example, x1 give me a y1. So I'm going to copy that equation down, except I'm going to change all the x to x1. I'm going to change all the y to y1. So that gives me equation number 2. Then the next step I'm going to check to do is to assume I have a different input. That will give me output. Again, this equation applies because it's the same system. We're applying the input to the same system. Of course, that equation will apply. Okay, so that again, I replace x, all the x's on the right-hand side by x2. Replace everything on the left-hand side by y2. I get equation number 3. As I've shown in the previous examples, the crunchy part is to check this. If x2 equals to a times x1, would y2 equal to a y1? That has to match for every single term, okay, in the differential equation. So I'm going to multiply equation 2 by a factor of a to every single term in the equation. So that becomes a there, a there, a there, a there, a there. And then I'm going to take 4 out of bracket, 5 out of bracket, 3 out of bracket, 2 out of bracket. Okay. So I get 4 brackets a y double 1 dot, y1 double dot, plus 5 brackets 5 y1 dot, plus 3 a y1 equals to 2 times a x1 dot equals plus a x1. So my checking is actually to check equation number 3 against equation number 5. Remember, every single term has to match. So I'm going to start from the right-hand side, x2. I have a x1, so that match. x2 dot, 2 times x2 dot, that equals 2 times a x1 dot. x2 equals to a x1, x2 dot equals to, therefore equals to a x1 dot. That also match. y2 equals to a y1, that match. That red equation there. y2 dot equals to a times y1 dot, again y2 dot equals to a y1 dot. y2 double dot, it should be a times y1 dot double dot, and in equation number 5 we have a y1 double dot. So every single term matches between equation number 3 and equation number 5. Therefore, the system defined by equation 1, the second order differential equation, is a linear system. Okay, so plenty of examples. That will be the end of this session, and I have some questions or practice questions for you guys to do before we move on to the next section. Thank you.